General relativity is the prevailing classical theory of gravitation, confirmed by numerous tests ranging from light deflection during solar eclipses to the recent high-precision measurements by radio interferometry. In these tests, scientists often design experiments with general relativity's predictions in mind, which can shape data analysis and interpretation. By contrast, quantum gravity, the unification of general relativity with quantum mechanics, remains unsolved despite decades of effort in approaches like string theory and loop quantum gravity. No candidate theory has yet produced definitive, testable predictions at accessible energies, leaving a conceptual and experimental gap at the Planck scale. While general relativity excels in its domain, quantum gravity remains one of modern physics' greatest unsolved problems. Scientists working within the framework of general relativity can unwittingly overestimate their knowledge of gravity because they rely heavily on a well-tested but incomplete theory, leading to several interrelated cognitive and methodological biases. Researchers may believe they fully understand general relativity's explanatory mechanisms until forced to articulate them in detail, a hallmark of the illusion of explanatory depth. This bias means that familiarity with general relativity's equations can mask deeper conceptual uncertainties about the nature of spacetime and gravity. Confirmation bias leads scientists to favor data and analyses that affirm general relativity's predictions, sometimes overlooking anomalies or alternative interpretations. For example, early eclipse expeditions, that is, Eddington's 1919 observations, were criticized for potential systematic errors and confirmation bias, though later reanalyses vindicated the results. All observations in science are theory-laden, shaped by the conceptual framework of the investigator. In general relativity research, measurement strategies, data calibration, and even which phenomena are deemed significant can reflect implicit general relativity assumptions. For example, modern radio interferometry tests confirm general relativity to high precision, but their design and data reduction still presuppose general relativity's framework, illustrating theory-laden methodologies. At the frontiers, such as searches for quantum gravitational effects, scientists face experimenters' regress. To validate an experimental result, one needs a theory, but to confirm a theory, one needs reliable experiments. This circularity can reinforce prevailing theories and delay recognition of new physics. Overconfidence bias can cause researchers to overestimate the accuracy and scope of general relativity, particularly when their domain expertise is deep but narrow. The Dunning-Kruger effect further suggests that those with limited insight into quantum gravitational issues may not appreciate their own gaps in understanding. Thomas Kuhn's concept of normal science describes how a dominant paradigm, here, general relativity, defines what questions are asked and how they are tackled. Paradigm lock-in can suppress radically new approaches needed for quantum gravity, delaying paradigm shifts until anomalies accumulate enough to trigger extraordinary research. To summarize, because general relativity is exceedingly successful in its domain, physicists may become overconfident in its completeness, underestimating the conceptual leap required for a quantum theory of gravity. This can lead to dismissing novel approaches that don't neatly extend general relativity and prioritizing anomalies that fit within general relativity's perturbative quantization, while neglecting non-perturbative or background-independent frameworks. The scientific community can better balance confidence in general relativity's achievements with openness to transformative ideas needed for quantum gravity, ensuring that self-deception does not stall fundamental progress.